was interesting, this title. Honestly, it should probably be called How Do Wi-Fi Services and Delivery Has Impacted the Development or the Influence of the Development of New NBaseT solutions. We're going to look at how Wi-Fi has advanced from the consumer model that we've seen over the last number of years to something more predominant for enterprise. We're going to also take a look at cabling solutions to see the impact of those. So when we start to look at this, how viable is Wi-Fi in the enterprise? That's the real question. Right? If we look at traditional Wi-Fi solutions, 802.11a, b, and g, those are consumer-type services, right? Residential. Almost everybody in this room probably has an 802.11g radio sitting in their basement somewhere, broadcasting within the house, right? And it's adequate. It's adequate, because what are we moving inside the house, right? We're accessing our internal network. We're maybe streaming some traffic across our network to our TV, to our media players, right? And then, of course, we're browsing, but when we browse, we're going out through our external network. How many have a pipe leaving their home that exceeds 100 megabits, right? So a G radio in your residence, more than adequate. But when we move into the enterprise space, is a 54 megabit pipe sufficient just on the wireless side? Right? And so that's been the transition. As we move along, we introduced 802.11n. And 802.11n brought us 450 megabits of bandwidth. So significantly more bandwidth to actually be able to operate in the enterprise space. It also introduced a number of other technologies that did not exist in previous generations of Wi-Fi. So for example, if we look at existing G radios, we ran into problems with dead spots within our facilities. Right? Everybody put a G radio in. We offer Wi-Fi in our facility, right? But not everywhere, because there were dead spots. And those were primarily created because we had a single antenna on our radio. It could only broadcast so far. We got multipath fading because the signal would reflect off the glass. To compensate for that, the power would be automatically lowered, but of course, as soon as we lowered the power, we had dead spots. So these were challenges. In 802.11n, though, we introduced new technologies, MIMO, multiple in, multiple out, right? The idea of being able to capitalize on those reflections and make use of those to enhance the signal. So that was one key feature. The backhaul rate for 802.11n, as we'll see a little further, the backhaul rate now exceeded our 10-base-T, 100-base-T data rates. So now we're getting into a data rate that actually is usable in the enterprise space. 802.11ac, wave 1 gigabit of bandwidth on the wireless network. Now we're getting into bandwidths that actually match or correlate to the wireline rate that we've been using for a number of years. Okay? So these are important changes. When we get into wave 2, specifically, we are now going to run into problems. And the problems are going to have to do with backhaul rate. Right? Not the wireless rate, but the backhaul rate specifically. A, B, and G radios. Number of significant problems, as I mentioned. First one, of course, speed. Right? 54 megabits on a G radio. What happened if somebody came in with a B radio and hooked up to your G network? Right? All of a sudden, you went from 54 megabits to 11. Right? And that's assuming they were close to the radio. If they were a long way away, you'd see your 54 megabits drop to 2. And everybody scratches their head and goes, what happened to the network? Right? We had one spatial stream, or one network, one transmission path. And that transmission path was dictated by the slowest person on the network. It was a half duplex network. We transmitted, we received, we did not do both. And finally, the multipath fading issue. With one antenna in an A, B, or G network, the signal transmitted in every direction. That was another issue. What's the most likely handheld device that we were using back when G was around? Our laptop. It only had one antenna. And so it was receiving signals that were bouncing off walls, off glass, okay? And it was trying to correlate what was the primary signal from what were reflected signals. And the only way to do that was to communicate back to the AP and have it lower its power so we could get rid of some of the reflected signals. All of a sudden, I got dead spots again. 802.11n, though, started to change all that. Number one, MIMO, right? We got rid of the whole issue of reflections. Number two, data rate went up. So we started to increase that. That was now usable. We also achieved more bandwidth, 40 megahertz of bandwidth capability. And that was going to help drive our speed back up and make it more useful. When we look at 802.11ac wave 1, 80 megahertz of bandwidth. We just doubled the channel width. The effect of that is going to be to double our data rate. And when we look at AC wave 2, again, we've doubled the bandwidth. Okay? So we're going to see some significant increases from that. And you'll notice here, maximum data rate, 600 megabits, and this is on the wireless side, 1.3 gigabit, up to 6.9 gigabits of bandwidth. So a lot of changes in the wireless arena. All right, so we've got more bandwidth. We've got, we'll say, new encoding schemes. We have these multiple transmission paths. Spatial streams, what are they, right? Well, spatial stream is nothing more than a transmission path. It's a method to be able to transmit data from an access point to an end user device. And the end user device can support multiple ones, potentially. End user devices must manage, though, three key features. The first one is processor performance. Now, today, almost without exception, I'm going to guess that everybody in this room probably has a smartphone, right? Does cellular, does Bluetooth, does near-field communications, and it does Wi-Fi, right? If I gave you a cell phone, for example, and that's your end user device, and you want it to go really fast, you need to have a fast processor. Well, if I got a fast processor, it's churning away data, what does it need? It needs a stronger battery to be able to handle that extra processing power. All right, so I need a stronger battery or I need a bigger battery. What happened to my cell phone? Right? Just got bigger. And my battery life will probably go down. Right? If I have the same size battery, battery life will go down. So now I have to have a bigger battery to compensate for that. But then, of course, that drives up the cost of the phone. Right? So this is a catch-22, except there's three parts to it. So we have to keep that in mind. The other thing that's also hidden in this is the fact that how big's our cell phone? Let me see if I can find mine here. Right? Here's my cell phone. How much real estate's on this? Keep it in mind right now, there's a cellular antenna in there, there's a Bluetooth antenna, there's a Wi-Fi antenna, and there's a near-field communications antenna. I got 4 antennas already in this thing, right? So I'm limited in real estate. I'm limited in real estate for the battery, antennas, and processing. So these are all challenges that go into the device. Mobile devices will likely only ever support one spatial stream, one transmission path because of that. Right? Unless we're all going to start carrying around spare batteries to be able to process all this, and something a lot larger than even my phone, one's about all you're going to have room for. But again, it's a true mobile device. If we start to look at tablets, bigger footprint, more battery power, more real estate space, right? more processing capability. If you look at tablets today, Microsoft Surface, for example, is it a tablet? Is it a computer? It has that capability, has the processing capability. So tablets will likely see 2 spatial streams. And keep in mind that each spatial stream is a transmission path. It's a full path. So you're going to get the full bandwidth available in that spatial stream. Laptops and desktops, multiple spatial streams, right? Because keep in mind, a spatial stream represents an antenna. I have to have an antenna for each spatial stream. Okay? So laptops, desktops, they have more footprint, they have larger batteries, more processing power. We can support multiple batteries or multiple spatial streams and antennas. All right. The wireless RAN, radio access network, versus the physical layer network. How does that work? Well, if we look at 802.11n, one spatial stream, 450 megabits of bandwidth across the radio, right, across the network, has a physical layer data rate of about 300 megabits. And today we can easily accommodate that on a gigabit link. No problem, right? 802.11ac, though, introduces multiple spatial streams, as I said. Each spatial stream will operate roughly 433 megabits, requiring a backhaul of 300 megabits on the physical layer for every spatial stream. So it will grow in multiples. But even worst case with 3 spatial streams, we're only going to need 900 megabits of backhaul. Easily accommodated on a gigabit link. Not just the physical Cat6 gigabit link, but the Category 6 or 1G NBase-T switch port. Right? So we're going to have to keep that in mind, that it's not just the physical layer, but it's the switching layer that we have to deal with as well. When we move to 802.11ac Wave 2, remember the bandwidth just doubled. It just doubled from 40 to 80, and from 80 to 160 megahertz. So we just doubled the bandwidth capability, we doubled the speed, and you'll notice the speed went from 433 to 875 megabits for a single spatial stream. The impact of this, of course, is as soon as we hit 2 spatial streams, we're at 1.2 gigabits of backhaul data rate. We now have a problem. Right? We now have a problem because all of our Category 6 cable and our switch port is only guaranteed up to a gigabit. What happens if we try and drive 1.2 down that pipe? Will it work? For a while. But all of a sudden, we're going to start getting packets queued up inside a buffer, and after that, what are we going to do? The system's going to start dropping them. And because it starts dropping packets, errors will be created, acknowledgments won't come back correctly, and the system will retransmit them. And then we will start to spiral, right? It's going to get worse. And why? Well, because we can only put 1 gigabit worth of bandwidth across there. And we've got a backhaul of 20% more. So we have a problem. How do we solve it? Well, we have to put in a 10G NBase-T link. And now we solve that problem. But it's not just a Category 6A cable we have to put in. We have to put in a switch that will support it as well. And so that becomes another issue, another cost associated with this. As we move forward through Wave 2, and we get into multiple spatial streams, we are going to have some serious problems. Right? And so that's the challenge that's ahead of us. How are we going to handle that? Of course, today's standards recommendations call for what? Especially on APs, specifically on APs. 2 Category 6A cables, right? Everybody clear on why now? Right? That makes sense? All right, so we've taken a look at wireless. We got that through our heads. We now see where we're going. Let's take a look at the cabling, though, the infrastructure, because that's what we're going to have to deal with. Cabling Installation and Maintenance Magazine in 2004 looked at a study, or did a study of the installed database. And what's interesting is about 74%, 74% of the installed cabling that's out there is Category 6 and Category 5E or less. Right? 74%. And take that one step further, Category 5E cable is almost twice Category 6. And just as importantly, it's almost 3 times Category 6A. So there's a lot of 5E cable out there, a lot of 5E cable. Not everybody's going to be looking to replace their 5E cable with 6A cable right away, especially for their access points. So that's the next challenge. Gigabit Ethernet. Gigabit Ethernet was originally designed to work on Category 5 cable. So why doesn't it? Right? And there's all sorts of reasons. Number one, how much bandwidth's on a Category 5 cable? 100 megahertz. All right? What's the encoding schemes? How good are the digital signal processors that we created almost 20 years ago? Right? So those were challenges. TSB 95 came along, and we got Category 5E cable. Category 5E cable did a couple of significant things. It gave us a little bit more headroom. Right? We can now support NBaseT on 5E cable. Okay, but 5E cable is supposed to be better than 5, and 5 was supposed to be designed to support Gigabit Ethernet. All those guys went back to the back room, they started arguing it out, and what did we come up with? We came up with a design called Category 6 cable. It had sufficient headroom, it had sufficient noise reduction, insertion loss, that we could now get Gigabit Ethernet across that with a safety margin, lots of headroom. Okay? And that was important. Since Category 6 cable was brought out and was designed that way, what else has happened? Well, we got 6A, designed the same way. The manufacturers of the PHY chips themselves, the cabling manufacturers, all get together. They both work it out and say, you know what, we can handle in the cable insertion loss. We can reduce the noise. We can reduce near-end crosstalk, right? We can have an impact on these things. The PHY chips, the digital signal processor guys, they looked at it and said, well, if you can look after that, we can look after this, right? We can develop chips that will do this, that will increase the data rate. They will operate within that fixed amount of bandwidth. We can put more bits per symbol within the transmission path, and we can achieve higher data rates at a lower frequency. That's significant. Interesting fact, in 2014, over 7 billion meters of structured cabling was sold globally. Okay? I know all the manufacturers out here, including us, would love to have sold the 7 billion, but we didn't do it all on our own. Right? 7 billion. What's interesting is this. The blue section is Category 5E cable. The red section is Category 6. This green section, 6A. I don't know if anybody can spot it. Category 7 is listed up there. Not really significant. Category 5E cable has been on the decline for the last, well, since 2009, well, really since 2004, but it's been on a very steady decline since 2009. At the same point, Category 6A cable has been on an increase. But even in 2014, twice as much Category 5E cable was sold globally as Category 6A. And we're going to try and put what data rates across our cabling? Right? We're going to try and get gigabit or better across this infrastructure. And yet, in theory, we're putting out a Category 5E cable at twice the rate of 6A. It's a problem. It's a significant problem. Study group was created back in 2014. We're going to talk about them again in another slide or two, but NBaseT. Everybody heard of them? Next Generation Enterprise Access Base-T Alliance. It's a title unreal. They looked at literally a year ago, January of 2015, they looked at the cabling that was being installed globally and determined, or tried to determine, how much of that cable was actually going in as new installs. How much of it was actually going in to replace or upgrade existing cabling? And they found that in North America and Europe, we tended to be leading the pack here at about 40%. So roughly 40% of the cable that was being purchased globally was for replacement of existing cable. So when we look at the cable numbers, Category 6 cable, 4 billion meters. We're going to ignore that for a minute, because the ones that are really important are Category 5E and Category 6A. Category 5E, 2 billion meters were sold in 2014. Of that 2 billion meters, roughly 40% was for replacement and upgrades. So 40% of 2 billion, 800 million meters. And that broke down at 500 million meters to replace Category 5 or less cable. So somebody was finally upgrading their Category 3 cable to Category 5E, right? More importantly, the other 300 million meters was just to replace existing Category 5E. So they didn't go anywhere. They just brought it back up to what it was. Why is that significant? Well, Category 6A cable. Category 6A cable, 1 billion meters sold in 2014. That means that 40% of that is roughly 400 million meters. Okay? Just keep that number in your mind for a second. 400 million meters is upgrades. But in Category 5A, it was 800 million. So Category 5A is being replaced, or Category 5A is 5E is replacing Category 5 and 5E cable at twice the rate of Category 6A cable. We're not really moving forward, are we? Okay. And if we look at 6A of that breakdown, look at this. 6A replacing 5E. Okay, that's a good step. 6A replacing 6. So most of the 6A that's going out there as a replacement truly is replacing 5E and older cable. Right? So we are making some headway, but not the size that we need to. And Category 6, of course, Category 6 is replacing 5 or less, 5E, so 36%. And again, we're putting in 4 billion meters of cable, Category 6 cable annually, and it's growing. And 36% of that is to replace 5E or less. And the 4% is just to upgrade existing 6 to 6. All right, so why is this important? Well, current cabling infrastructure, right? The impact of it on future networks, as I said, when we look at Wi-Fi specifically, we need to get beyond 1 gigabit. Cabling standards today support fixed bandwidths. Right? Everybody knows what's the bandwidth of Category 5E cable, what's the bandwidth for Category 6, for 6A, for Category 8. Right? We know what those bandwidths are. Switching technology supports fixed data rates that operate within those specs. We know that we can get 100 megabits or 100 base T to operate on a Category 5E cable because it's got 100 megahertz of bandwidth and we're golden. Right? Cost to upgrade the infrastructure. We've got to get that 1 gig, we've got to get that 100 base T cable out of the system so we can put in 2 6A cables. But it's not just the 6A cables, right? It's the switch we've got to change too. We have to upgrade both these pieces. And the cost to do this, imagine you want to bring your wireless network up to 11AC, wave 2. You want to be out there on the edge. Your existing infrastructure, though, is 5E. What are the switches you have? 10100s, right? 100 base T. You might have gigabit switches, even though your cabling is only 5E. But to support the 10 gig of the 6A cables for AC, you now have to go out and get new switches to be able to support it. So the cost to do that may become prohibitive. ISO working group last year put a recommendation forward to set Category 6 as the new minimum standard for horizontal cabling in office space. It will likely be adopted. What does that mean? Well, it means that 5E goes away. Sorta, right? It's a recommendation, right? It's a recommendation. Finally, future networks are going to require more flexibility, right? Not just in the cabling, but in the switching technology. Both of these things have to work together to be able to move us forward, right? We don't want costs necessarily to be the determining factor of whether or not we can move forward, especially if the cabling infrastructure, I just put my 5E cable in, why won't it work? October 2014, the NBaseT was formed. 4 small organizations, Cisco, Aquantia, Freescale, and Xilinx, got together and said, hey, we're the best in our organizations. We can come up with a way to solve this problem. We can look at the cabling infrastructure. We can look at the physical layer, the transmission, the PHY chips, right? We can come up with a way to get more bandwidth out of that existing cabling. They had a couple of objectives. Number one, data rates. They wanted to improve the data rates. Right? They had to look at how they could do that. And again, we had PHY chip manufacturers. Remember, the PHY chip manufacturers worked with the cabling guys to develop Category 6 and Gigabit Ethernet. They worked with the cabling guys to develop 6A, to develop Category 8. All of these guys worked together. So this was not impossible. They also set, beyond the data rates, PoE. They wanted to still be able to support PoE because we're going to have lots of devices out there that will be PoE driven off those same switches, so it had to be supported. And it wasn't just PoE, but PoE plus and 4-pair PoE, right? All 4 of these things. As of the end of last year, the organization was roughly a year old, over 45 members, all on board now, trying to figure out how to do some of this stuff. All right, so what is multi-gigabit Ethernet? No short answer, but we'll try and give you one. It's new data rates. It's new data rates that will support on Category 5E and Category 6 cable, 1, 2.5G, and 5G NBaseT. Right? So brand new data rates. Imagine getting 5 gigabits of data rate on your existing 5E infrastructure. Now, we didn't solve all the problems, right? We still have to change the switch, right? The existing switch that you have will not perform this, right? So you still have to, what you did do, of course, is you postponed recabling your facility. You can reuse that existing cabling. Category 6A, of course, it can do 10G NBaseT today. It will be able to handle the intermediate speeds as well. Okay? So that's one of the key advantages. PoE, as I said, PoE plus and 4-pair PoE. These are all the capabilities within the NBaseT solution. How does that impact us? Well, if we look at today's transmission methods and coding schemes, and we look at 100 NBaseT, 100 megabits of throughput, 2 pairs are utilized, right? 2 pairs. We got 4 pairs in the cable, but we still only use 2 pair for 100 NBaseT. We have a transmit path, we have a receive path. We do not do both of them simultaneously. They are separate paths, right? What's interesting is the far right-hand column, the symbol rate, 125 megabaud. Okay? 125 megabaud. That's the symbol rate. Within the symbol rate, each symbol represents 0.8 bits. I don't know how we fractionalize it, but 0.8 bits, all right? And if you take 0.8 times 125, 100 NBaseT. Okay? All right, so everybody remember their early electronics, telecommunications, right? Everybody remembers what Nyquist theory is. I'm sure you all do, right? Nyquist theory. Nyquist frequency is half the data rate. The data rate in this case is 125 megabaud. So the frequency is 62.5. What's the bandwidth for category 5E cable? 100 megahertz. So clearly we're well within the range of the cabling. If I take that same cable, essentially, and instead of sending 0.8 bits per symbol, I send 2 bits per symbol. 2 times 125 is 250. I've got 4 pairs. I make them transmit and receive simultaneously. So now I have 4 pairs at 250. I have 1,000 base T. That's simple, right? So now I have a functional system. I've got 10, I've got 100, I've got gigabit Ethernet, or 1G base T. If I take that same cable, that category 5E cable, and instead of running at 62.5 megahertz, I crank the data or the frequency up to a full 100 megahertz. I use the capability of the cable. If I do that, my baud rate will go up. It will double. This is where the 5-chip guys come in, because they come up with a way to say, okay, I can work with 200 megabaud, and if I can insert 3.125, 3 1/8 bits into every symbol, what will I create? I will create 2.5 gigabits of bandwidth. And I'm still operating on a category 5E cable. Right. If I take that to a category 6 cable, where I've now got more bandwidth available, I now push 5 gigabits of bandwidth through that category 6 cable. Okay. And again, if you go back to that slide ahead, we're going to see it again shortly, but that slide that indicated that for wave 2, I need upwards of 6.9 gigabits of radio network, which translates to 4.8 gigabits of wireline data rate. I now hit 5G. I'm good. All right? Of course, 10G base T is still 400 megahertz, 800 megabaud. There's our symbol rate. We're good to go. Think about, real quickly, do the math. There's going to be a test, right? What time is it? If I take that 400 megahertz and I push it up to the limit of category 6A cable, right? 500 megahertz. Double that to get the baud rate, that's a gigabaud. If I even do nothing else in terms of the bits per symbol and I operate at 3 1/8 times a gigabaud, right? I am now operating at a 30 gigabaud or 30 gigabit data rate on my cable. That's what's going to be important. We now have the ability to push 10G base T up to 30G. Will that happen? I don't know the answer on that one, sorry. Okay, so these are the changes. These are the changes that we're seeing right now and how they're going to impact us. All right, so here's our table back. Gigabit serving all the way up to 11 AC wave 2, 1 spatial stream. We're good to go. As soon as we hit wave 2 with 2 spatial streams, in the past, it was looking like we were going to have to use a 10G base T type solution. Change our switch, change our cabling, and we're good. However, what has this change meant for us, these new NBaseT solutions? It means that we can do the 1.2 gigabits on a 2.5G base T solution. We can do 4 spatial streams, which are 2 gigabit of backhaul on 2.5G base T. And we can, of course, do 8 spatial streams, 4.8 on a 5G base T. We've now solved the problem, and we're using our existing infrastructure. We still have to replace our switch. That's not going to go away. But we don't have to change that cabling. And as cabling manufacturers, we're always telling people, right, You put in the cable in, you're putting it in for the next 20, 25 years. Right? And so we truly are doing that in this case. However, what's the recommendation? Right? 2 6A cables. 2 6A cables. And again, think about it, because we haven't talked about this guy, but he's coming. Right? He's coming. All right, so what's the impact? Right? That's what we started off with. That was the impact. What is the impact of NBaseT on Wi-Fi? And I'm going to start on the Wi-Fi side. On the Wi-Fi side, right, wireless rates 1.3G, 6.9 on the wireless side, that translated into a 1G uplink or a 5G uplink, 4.8, right? But on the NBaseT side of the house, what do we get? We got multiple data rates, 1, 2.5G, 5G base T, and of course, reliably, 10G base T. We've got support for PoE, PoE Plus, and 4-pair PoE. Right? So we can support the PoE solutions. And what's really important is the auto-negotiation. Right? The devices will auto-negotiate. They're going to look and measure the insertion loss and the noise level, the signal-to-noise ratio, right, to determine what will be their maximum data rate. And that's what they will operate at. If the noise level increases, they will negotiate down. If it clears, they'll negotiate back up. Right? So these are the kinds of features that we're going to see in these switches. What about the future? Right? What about the future? We have to be able to support going forward because something's going to change. Right? I didn't talk about that last line for a reason. 10 gigabits of wireless throughput. All right? I'm not sure my cell phone can handle that. But what's that going to mean to us? It's going to mean that the desktop's going to have to do the processing. We're going to have something a lot stronger. It's going to have multiple antennas. It's going to need more power, more processing capability, right? And more footprint space. It's going to mean the access point is going to have the capability of moving that amount of data out to the access point to be able to transmit it. Multiple spatial streams. Multiple spatial streams are going to be important in this network because we're going to use directed streaming. We're going to use multiple antennas to actually direct the power to a specific user. And if I've got multiple antennas, I can do that to multiple users simultaneously, or I can take all the antennas and use them and direct all the spatial streams to a single user. So that's the kind of capability we're going to have. Existing cabling, 5E and 6, of course, all right, this is it. I don't think we're going any further with it, right? It's going to get 2.5, it's going to get 5G base T. We're probably pushing the end of it. Keep in mind that that ISO working group is saying that's it for 5E, right? Can we get more out of 6? Probably, right? Because it was designed differently. Can we get more out of 6A? Definitely, right? And of course, we're already looking at Category 8 as a new standard. I'm not going to be the only one that says this. Not all cables are created equal, right? Not all cables. We've got 5E cable out there that we know just is not going to cut the mustard. It's going to have to be replaced. Whether we replace it with existing 5E, move it up to 6 or 6A is irrelevant, but not all cable. We can't go out there and say, you know what, manufacturer said this will run on 5E cable. Yes, but he probably put limits on terms of noise and insertion loss as to whether or not it will work at these data rates. So keep that in mind. All right, well, with that, I want to thank you. Hope it was informative.